Imagine a network without spanning tree, where switches are wired in loops and frames don't stop. One broadcast turns into a storm, flooding every port, then circling back again and again. Users get disconnected, calls drop, the network goes dark. Users become angry. And guess what? They're coming after you. Your cell phone starts ringing. In fact, your cell phone doesn't stop ringing. And the worst part? It looked like everything was working, right up until it wasn't. Spanning Tree Protocol, or STP, is a layer 2 protocol with two jobs. Number 1, preventing loops. And number 2, allowing redundant paths. In many newer designs, other technologies handle redundancy, and STP becomes a safety net. And just a heads up, when I say bridge in the context of spanning tree, just think of it as another word for switch. So here's the spanning tree process in 5 steps. Step 1, elect a root bridge. Just like in high school, somebody has to be the center of attention. Step 2, we have to pick the ports that get to root the quickest on each switch. These are the root ports. Step 3, now designated ports are chosen, and on the root switch, all ports are designated ports. Step 4, leave redundant ports in blocking. These are the gremlins that cause loops. Block them, and loops never form. Step 5, monitor and adjust. STP keeps an eye on the network and makes adjustments as needed. It's always watching. The way switches communicate in spanning tree is through BPDUs, Bridge Protocol Data Units. The root bridge sends out configuration BPDUs every 2 seconds by default, according to the hello timer, through its designated ports. And because of that, when a new switch powers on and thinks that it's root, it also starts sending out BPDUs. In the BPDU frames, the fields that we care about for now are the root ID, which identifies the current root bridge, the root path cost, which is the total cost to reach the root from the sending switch's perspective, the bridge ID, which shows who sent the BPDU, and the port ID, which tells us which port it was sent from. Also, all the spanning tree timers get set inside these BPDUs. So if only the root bridge sends out BPDUs, then how do they reach the whole network? Well, that's a great question. The root bridge is the only switch that originates config BPDUs and sends them out at regular intervals. When non-root switches receive one on their root port, they create a new BPDU. They add their own port cost to the path cost, insert their own bridge ID and port ID into the appropriate fields, and send that new BPDU through their designated ports. So the result is configuration BPDUs flow down from the root step by step until they reach every switch in the network. But don't worry, non-root switches get their own exclusive job too. They're the only ones that can originate topology change notification BPDUs, the other kind of BPDU. So a root bridge has to be elected, but how does that happen? Well, in the simplest terms possible, the switch with the lowest bridge ID becomes the root bridge. A bridge ID or bid is a field in the BPDU frames that switches send out. The bridge ID is 8 bytes total, and it's made up of 2 main parts, the bridge priority, which takes up 2 bytes, and the MAC address, which takes up the remaining 6. But there's a twist. Those 2 priority bytes are actually split. The first 4 bits are the priority value, and the next 12 are the system ID extension, which sounds complicated, but it's really just the VLAN ID, which in this case is 1. Since this bridge priority only uses the first 4 bits, it can only be in increments of 4096, as you can see here. See, every switch starts out thinking that it's the root bridge. Kind of like in high school, every kid starts out thinking that they're the most popular. Well, I didn't, but a lot of people do, right? Also, most brands of switches set the bridge priority to 32768. So if everything's set to default and the priority is the same and the VLAN is the same, what determines the root bridge? Well, probably you've guessed it by now, or maybe you know it, but it's the MAC address. And when it's something as arbitrary as the MAC address picking the root bridge, many times that's just not a good choice. And if you saw my switches and VLANs video, this is what I meant when I said that you probably want to select your root bridge manually. And here's one way to do it on a current Cisco switch. Now that we elected a root bridge, each non-root switch has to select its root port, the port with the lowest total cost back to the root. Root bridges don't have root ports. After all, they are the root, so they have no path leading back to themselves. Here are the path costs for traditional spanning tree. Remember, these are a part of the BPDUs and are used in deciding root ports and designated ports too. If two root ports have the same cost, there are a couple of tiebreakers switches can use, but let's look at a simple case first. On switch 2, figuring out the root port is pretty straightforward. The top port has a root path cost of 4, and that's because it's a 1 gig link, and 1 gig links have a cost of 4. The bottom port has to go through 2 other switches, so that's 4 plus 4 plus 4, a total of 12. So the top port wins. It has the lowest cost, so that's the root port. Switch 3, same story. Top port cost is 4, bottom port is 12, so the top port is the root port again. But switch 4 is a bit different. The root path cost on the left port is 4 plus 4, so 8 total. And the port on the right is also 8 total. So in this case, we need another factor in root port selection. It will be the switch port with the lowest sender bridge ID. Remember, bridge ID is priority plus VLAN plus MAC. So if we are on switch 4, the BPDUs that we're getting from switch 2 and switch 3 both have the same priority and the same VLAN, but switch 2 has the lowest MAC address. Therefore, it has the lowest and winning bridge ID. So on switch 4, the port on the left side that is facing switch 2 becomes the root port. So here are the tiebreakers for root ports. It's a decent reference if you want to take a screenshot. The main thing to remember with root ports is that they're chosen per switch. After the root ports are selected per switch, designated ports are selected per segment. Segments in this context mean the connections between switches. Each of these are segments that I'm highlighting here. There is one designated port per segment, and designated ports, like root ports, always forward traffic. So on each segment, the port with the lowest cost to the root bridge becomes the designated port. Any port on a segment that is not a designated port or root port gets blocked. All of the ports on the root bridge become designated ports. For the segment between switch 3 and switch 4, the root path cost is 4 on the switch 3 port versus 8 on the switch 4 port. So the port on switch 3 becomes the designated port. It has the lower cost to the root. And finally, on the segment between switch 2 and switch 4, the port on switch 2 has a root path cost of 4 versus the root path cost of 8 on the switch 4 port. The port on switch 2 becomes the designated port. Again, it has a lower total cost to root. So we selected our root ports per switch, and we selected our designated ports per segment. So now it's time to stop the loops by making sure that any port that's not root or designated stays blocked. On the segment between switch 3 and switch 4, the port on switch 4 stays blocked. Sometimes we like to think of a link getting blocked with spanning tree, but it's really just ports that get blocked. Remember, we said that designated ports always forward, and the designated port on switch 3 is forwarding to switch 4. But switch 4 is just dropping the traffic since the port is blocking. But switch 4 is not dropping BPDUs. Even when it's blocking, it needs to see those. So if a link goes down, it will spring into action, unblock, and become the designated port for that segment. And let's also not forget that the root port moves for switch 3. Here are the tiebreakers for designated ports. It's a decent reference if you want to take a screenshot. The main thing to remember with designated ports is that they're chosen per segment. Now let's talk about spanning tree port states. You can think of these port states as the different phases of spanning tree. One of the states is disabled. That just means the port is shut down or STP is turned off. It's not even part of the spanning tree. STP completely ignores it. The first STP state is blocking. This is how loops are prevented, and a port can stay in this state forever. It receives BPDUs, but doesn't forward frames or learn MAC addresses. The next port state is listening. Ports in this state receive BPDUs and can send them too. In this state, a port does not forward data frames, so loops are still prevented. After that, we have the learning state. Again, still receiving BPDUs, but also the port is learning MAC addresses in this state. And the last state is forwarding, where the port actually starts forwarding traffic. In classic spanning tree 802.1d, default timers make going from listening to learning states and from learning to forwarding states each last 15 seconds. Alright, let's dive into what spanning tree protocol is up to when everything is running smoothly. This is called the steady state or converged state, where all switches have agreed on the root bridge and the best paths to reach it. First, we have the BPDUs or bridge protocol data units. These are sent out by the root bridge every 2 seconds, like a steady heartbeat, keeping the network in sync. As these BPDUs arrive, each switch is constantly comparing them with other BPDUs received on every port, always making sure that it has the best route and the best possible path to route. Now, if a switch stops receiving BPDUs on the root port, the message H timer, typically set to about 20 seconds, keeps counting from the last BPDU received. If it reaches the max age without a new BPDU, that path is considered invalid, and the switch searches its other received BPDUs for a new root port. And it picks the next best one, which in this case is port 3, because port 3 has the lowest root path cost of all the BPDUs the switch is still receiving. So port 3 becomes the new root port. If a switch stops receiving BPDUs from the root on all ports and the max age timer expires, it assumes the root is gone and starts sending BPDUs naming itself as root. Other switches do the same. This is the same as a root bridge election. All of the switches start comparing BPDUs, and the one with the lowest bridge ID becomes the new root. The network reconverges from there. Once the network is stable again, it stays in that steady state until something changes. So here are 2 bonus questions for you from this section. I always like making and solving little puzzles. Hopefully you do too. The first one, why did switch number 6 become root? And the second one, why did the ports on switches 2 and 3 become designated and not the ports on switches 4 and 5? If you know, comment with the answer. Everything you need to answer these questions is in this steady state section of the video. Thanks for watching. Hey, I hope you enjoyed this video as much as I enjoyed making it. If you did, don't forget to like the video and subscribe to the channel, or share this with someone who needs it or might like it. There are a few people out there that comment on almost every video or every post that I do, and I truly thank all of you. You have no idea how much that helps out. I'm trying to decide what video to do next. Maybe a good Wireshark video? Maybe cybersecurity? The basics of Nmap? We exploit some vulnerability? Maybe routing? BGP? EIGRP? This channel is for you, so let me know what you want to see. And until next time, I'll see you in the next video.